live stream on YouTube go as well. Just 1 second. Okay. Right, so today we have Alexandre Barreira, who is an Origins Fellow at the Ludwig Maximilians University in Munich. And Alex was a postdoc researcher at the MPA a few months ago, if I'm not mistaken. And today he's going to give us a talk about connecting the visible universe to the dark, recent advances on galaxy bias prediction. So thank you, Alex, for accepting the invitation. And feel free to start whenever you like.
Okay, thanks a lot for the introduction. Good day and hello to everyone. So thanks for the invitation. I'm very happy to be giving this talk. Obviously got that it cannot still be in person, but I fingers crossed that things get better soon and we can see each other in person in some conference in the near future. I'm sure we've all been much looking forward to that. Okay, so this is the title of the talk, Connecting the Visible Universe to the Dark. This is going to be about some recent numerical advances with some results with predictions for galaxy bias, which as some of you probably know is a way to connect the visible universe to the dark, but I will be introducing these topics a little bit better as I go along. You seem to be a small enough group of people. Feel free to interrupt at any point with questions as I go along. The more interactive this is, I think the more interesting it is to everyone. All right, so I like to start with a simple and gradual motivation to the problem that I would like to solve. And a good place to start is always with a reminder I find of the current standard model of cosmology that we call them the CDM, and which we can group into which we can organize into 5 main ingredients. So here on the left, we have particle physics, or better said, known particle physics, because cosmology requires us to go beyond that. And in cosmology, we are a little bit sneaky and we just crudely refer to this as the baryons, but of course, there's more to it. And also in cosmological context, photons and neutrinos are also very important. The lambda here at the top is the infamous cosmological constant that, as we know, is what plays the role of the dark energy in this model to drive the accelerated expansion of the universe. CDM stands for cold dark matter, the dominant mass component in the universe. This is what sources predominantly the gravitational potentials inside which the particles we know can cool to form stars and gas that lives inside galaxies and clusters. Inflation is the name that we give to whatever happened at the early universe, some period of exponential expansion that is originally invented to solve the classical flatness and homogeneity problems, but nowadays we probably need it more pressingly to explain the origin of the primordial density fluctuations, which are the seeds for the structures we observe today, and then general relativity is the theory of gravity in this model. So as right at the top, there's a reason why this model is the standard. It fits the data pretty well. The emphasis on the word almost is just to guard against a number of recent observational tensions that have been causing some discussion recently. So things like the H0 tension or the sigma 8 tension. But even if the model was completely perfect fit to the data, we should, as scientists, that's what we do. We try to find cracks in the status quo and hope that will give us clues for new physics. And that's something we can still do. So to go through a really incomplete census of some of the open questions. For example, here on the particle physics side, cosmology is actually still the best tool we have to go after the absolute scale of neutrino masses. Sure, we have to make some assumptions here and there, but the tightest constraints still come from cosmology. Concerning dark energy, well, just because lambda is the simplest explanation, that doesn't automatically make it right. There's a lot of work on model building and on observational tests of dynamical models. CDM, I think it's fair to say that most of the community believes it's a particle, but we're still pretty much clueless about its mass and whether it interacts with any other corners of the model. Inflation is the bit we're going to touch on a little bit more hands-on towards the end of the talk. A current open question concerns the number of degrees of freedom that were present during inflation. This is something that can be probed with searches for local primordial non-Gaussianity. And in this model, finally, of course, GR is the theory of gravity, but there's a lot of work, especially at Queen's Mary on studying theories of gravity beyond Einstein's GR, or modified gravity models, as they are called. So these are some of the questions that we can try to answer. The good news is that there's a lot of data for us to play around as we search the answers to those questions. Here's a census or a collection of some of the most notorious data sets. Of course, on the left, we have the CMB. I'm writing there is probably the best data set we have so far, in that it's what provides most of the support for the establishment of the limited model as the standard. Then, of course, we have type 1a supernovae, notorious for providing the first concrete evidence for the accelerated expansion of the universe at low redshifts, and nowadays also very much at the heart of H-naught tension discussions. And then finally, here on the right, we have logical structure, which is the area I work on. This is what this talk is going to be about. And I'm writing here that this is probably the type of data where we have most potential for discoveries. This is not necessarily because logical structure is a better data set in itself compared to the others, even though one can probably try to have fun arguing that way over drinks, but simply because compared to CMB, for example, the logical structure analyses are not as evolved, so there's more territory to explore, and as a result, more potential for discoveries. So this is how we think the logical structure forms and evolves. This is realistic in that it comes from a realistic n-body simulation of structure formation in the universe. I'm going to play the video one more time just to be sure. So the universe, let me do it. The universe starts close to homogeneous, but there are tiny fluctuations, which are the things that are left behind by inflation. So some regions start off with more mass, and then they attract even more mass. And then at the end of the day, you end up with this filamentary structure that we call the cosmic web, where you have mass flowing along these filaments. These filaments surround empty regions that we call voids. And where these filaments intersect, like in this zoomed in region over here, we form these very massive gravitationally bound objects, which are the good old dark matter halos. So this is the object we're given in logical structure studies. As we just saw, this forms primarily under gravitational instability out of the primordial density fluctuations generated during inflation. It's a very nonlinear and non-Gaussian field. So the density contrast here spans many orders of magnitude. And by eye, you can clearly see that this is not a Gaussian random field. And it's also full of features. Right? This is a very distinctive field, and you can use many of these features to constrain effectively all of the main corners of the standard model, that being dark energy, dark matter, inflation, neutrinos, or the theory of gravity. But now getting to the problem I want to solve here. So the fact that this field is nonlinear and non-Gaussian actually already makes our life in terms of modeling it and making predictions for it extremely difficult. But if that wasn't enough, our life is made even harder by the fact that we don't even get to see this large-scale structure. So this has, of course, to do with the fact that most of the mass density in the universe is in the form of dark matter. That's the reason why dark matter is called dark. It doesn't interact, at least strongly, with light, so we do not see it. And so we are posed with this outstanding challenge of having to infer the whole thing, but we only have access to about 15% of it in mass, which is what's in the form of stars and gas that lives inside galaxies and galaxy clusters. So rather than this very distinctive field, our observations look a little bit more like this. So this is the same simulation data. In one case, I'm showing all of the mass particles. In the other one, I'm just showing the ones that form stars. And I think it's very instructive to flip between these two scenarios to help appreciate how much information is lost when we restrict ourselves to the visible part of the universe. So here are the two pictures side by side. So stars are not the only visible tracer we have of the logical structure. Another one that's very popular as well at Queen's Mary is neutral hydrogen, which you can probe with 21 centimeter line intensity mapping experiments. So here I'm zooming in on this, on the left on this dark matter halo. And where I have a large concentration in total mass, I also have a large concentration in stars, but I don't have any H1. So this is, of course, The physical reason for this is because in regions where I have strong star formation, I also make it easier for the gas to be ionized. So there is gas in this region here, but it's ionized, so it doesn't emit 21 centimeter photons. But the key point here is just to help appreciate that depending on how I choose to observe the universe, I'm probing sometimes in very qualitatively different ways the underlying density field. Let's just have a look at a couple more of these figures. So here I'm marking on the right the location in this simulation, which is called Illustrious TNG. I'm going to introduce it a little bit better later on. So now you can see the location of these quenched galaxies, which are these very big red ellipticals that are not forming stars in any significant way, and we can compare that with their star-forming counterparts, which are these bluish spiral galaxies that resemble our Milky Way. Again, you can see similarities between the two distributions, but they're not exactly the same. Here are all the galaxies with a stellar mass larger than 10 to the 9, 10 to the 10, and 10 to the 11. And here we can already learn a few things about this visible and dark connection. As I make a more aggressive mass cut, I end up with fewer objects because there are fewer massive objects in the universe, but the ones that remain are also more biased, and bias here is a keyword, towards the higher density regions. This is the case of blue galaxies, red galaxies. We can skip this. The key point is that at the end of the day, we're posed with this problem of having to connect the visible to the dark universe. The dark is what contains most of the cosmological information we are interested in. And then, of course, in order to access this information from our observations, this connection is something we have to understand very well. This connection has a name. It's called galaxy bias. And it's what I would like to tell you about in this, or what this talk is going to be about. So this is the rest of this. It's going to have 3 parts. I will continue by saying a few more words about galaxy bias, making its definition a little bit more precise. Then I will skip to what is the main part, where I'll show some results obtained with 2 methods called separate universe simulations and field level forward models. So this is where we're going to see results with predictions for galaxy bias using hydrodynamical galaxy formation simulations. And then I will end with some consequences for tests of cosmology, in particular tests of inflation through searches for local primordial non-Gaussianity. Okay, so starting off from the beginning, what is galaxy bias? So in a sentence, if I have to define galaxy bias in just a simple sentence, I would say that, or we should think of galaxy bias as being the answer to this question: how does galaxy formation depend on its dark environment? And long story short, the answer to this question comes in the form of an equation that is called the galaxy bias expansion. So this is such an important one. So let me describe it with the due time. This talk doesn't have too many equations. I think this might be the only slide with equations. So what we have here on the left, this is the local galaxy number density. So this is the number of density of galaxy that you would count at position X in some volume centered at that position. And you want to relate that to the global galaxy number density, the cosmic average. And then we parameterize fluctuations around the mean through 2 terms. The one that's going to be of interest to us is the thing that's inside square brackets. And what we have here is an expansion in perturbations or operators O, which describe aspects of the large scale structure that you suspect can have an impact on so this describes large scale perturbations in the large scale structure that you suspect can have an influence on the formation of the galaxies inside them. So this will include, as we will see, things like density fluctuations and tidal fields, and in cases where we're constraining local primordial non-Gaussianity, the gravitational potential is also important. And so what you have to do here is to just write down this list. And once you're happy with the level of completeness of that list, which depends on the exact application of mine, you multiply all of these terms by coefficients that we call the bias parameter. And then this equation makes apparent to the physical meaning of these parameters as the response of galaxy formation to changes in the amplitude of the several perturbations that each multiplies. Now, finally, just for completeness, this is important to mention. Galaxy formation depends on more than just large-scale features in the large-scale structure. The smaller scale details also matter, and this is what is described by the stochastic or shock noise contributions. So this is important to mention, which is what I just did. It's also important to take into account when we make predictions for galaxy clustering, but in this talk, I'll focus only on the bias parameter part, which is also called the deterministic part of the galaxy bias expansion. So to say exactly the same thing, but just with the help of this cartoon, what this equation is telling us is that at cosmic mean, galaxies would be uniformly distributed. Around cosmic mean, we can split our perturbations into two types, short scale and large scale ones. The short scale are these stochastic contributions. They tell us whether a galaxy forms in one location and not its immediate neighbor. And then we have these longer wavelength perturbations that modulate in this coherent manner the local number density of galaxies. And the strength of these modulations for all of the various types of perturbations is what is controlled by all of these galaxy bias parameters. So if you happen to have a tracer or some galaxy type for which the bias parameters would be 0, this means that your galaxy couldn't care less if the perturbation is there or not. So the galaxy number density is uniform, irrespective of the amplitude of the perturbation. Positive bias parameters means you're positively biased towards regions where the perturbation is positive, but the bias parameters can also be negative, which means the perturbation destroys the tracer you're interested in, and therefore you find it in more abundance where the perturbation is negative. So what are the two main reasons to study galaxy bias? So there are at least two. So when we make predictions for our galaxy observations, we will encounter cosmological parameters alongside galaxy bias ones. They're often degenerate, they have similar effects. And so reason number one is the greater our knowledge of biasing, the more chances we have at breaking some of these degenerate effects and obtain improved constraints on cosmology. You can turn the argument around, however, if you're more astrophysics, if you're a more astrophysics-minded person, you can take your galaxy data, take some priors on cosmology from other data sets, for example, the CMB, fit for the bias parameters. And since the bias parameters, as we just learned, are this way to describe the galaxy environment connection on large scales, you can hope to learn a few interesting things about galaxy formation and evolution in this way. So here's an example of a bias expansion for us to understand how these things work, and for me to introduce also some of the parameters I'm going to be showing results for next. So we have here 5 terms, and here I'm restricting myself to showing only the deterministic part of the bias expansion. So I'm not writing any stochastic terms. So we have written here down 2 terms associated with mass density fluctuations, B1 and B2. So you notice B1, think of it as being the first order derivative of the galaxy number density to changes in delta M, and B2 is just the second order derivative. So you can think of this as a Taylor expansion in the amplitude of all of these perturbations. The tidal field Kij squared appears at second order. So Kij here is the traceless part of the tidal tensor. It's a tensor, so I have to contract it at least once to form a scalar, which is why the tidal field only appears at second order. And also important, we have these B phi and B phi delta parameters, which are important when you're trying to constrain FNL, and in this case, the relevant perturbation is the primordial gravitational potential. So now we have these 5 parameters, and it's actually the case that for these 5 parameters, we have a pretty good understanding of the bias of these values for the case of dark matter halos in gravity-only simulations. However, I'm sure you'll all join me in saying that this is not yet sufficient. This is not the end of the line because we don't observe dark matter halos. Ultimately, we are interested in studying the bias of the galaxies and the gas that lives inside those halos. So there's a reason why a very simple reason why galaxy bias studies are lagging behind studies of halo bias, and the reason is because galaxy formation simulation is a lot harder than simpler simulation of halo formation, which requires you to solve only for gravity. Fortunately, over the last 5 or 10 years, a number of groups have been developing quite realistic, or the first realistic n-body simulations of galaxy formation in volumes that we can start calling cosmologically representative, so reaching the 100 parsec or 300 parsec mark. And it's after the development of simulations like this that the door to study galaxy bias and not just halo bias has sort of opens. So yeah, so now I get to the second part of the talk. So this interest of mine in studying galaxy bias is very much a research program that's in progress. We have already, though, a number of concise results, which is why I can give this talk already. So the results we'll see were obtained with a specific galaxy formation model. It's called illustrious TNG. If you're familiar with it, you're already familiar with it. If you're not, the key point to note is that this is one of the state-of-the-art models of galaxy formation and evolution in cosmological volumes. So the galaxies form and evolve under the action of gravity, hydrodynamics, as well as sub-resolution or subgrid prescriptions for physics like of gas cooling, star formation, stellar feedback, and the seeding, the growth, and also feedback by supermassive black holes. And this model was calibrated to match a series of key observations, so things like the cosmic star formation history and the Losey stellar mass function, the abundance of galaxies as a function of their stellar mass. So I'm going to show you results which were obtained using two methods. One is called separate universe simulations, the other one is called galaxy forward modeling. And what I'm going to do next is go in turn through each of these methods, describe the main idea behind them, and the key results we have obtained thus far with them. And I'd like to start with the separate universe side. So the key idea behind the separate universe method rests on top of this thing called the separate universe ansatz, which is what is written at the top of this slide. Let me spell it out for you. So this states that local structure formation inside long wavelength perturbations in some fiducial cosmology, this is equivalent to structure formation without any perturbation, but in a modified cosmology. So the key, so this cartoon here probably makes things more intuitive. Imagine a galaxy forming inside this box. The galaxy cannot tell the difference between what the separate universe ansatz states is that the galaxy cannot tell the difference between forming in this scenario or in a scenario where there is no perturbation, but the galaxy is in a different cosmology. So the key assumption that's being made here is that galaxy formation can be approximated as being local, and so this perturbation here is regarded as having an infinite wavelength, and an infinite wavelength is just a change in the background. A change in the background is a change in cosmology, separate universe. That's where the name comes from. So the key advantage that's worth highlighting of this method is that since you're able, through the separate universe trick, to embed your simulation volume inside the large-scale perturbation, and remember, biasing is the response of galaxy formation to large-scale perturbations. Since you can do this, your simulation itself does not need to be large to encompass the large-scale perturbations. And this is a special advantage that's worth highlighting, especially in the context of galaxy formation simulations, which are still quite expensive. And this is definitely an advantage that should be highlighted. So long story short, if you want to make a prediction for a galaxy bias parameter using this method, what you have to do is to run at least two simulations, one with a set of cosmological parameters that mimics a positive perturbation, another one that mimics with a set of parameters that mimics another value of the perturbation, and then you simply count the number of galaxies in these two simulations, take the ratio of that, normalized by the amplitude of this perturbation. So I'm just evaluating a finite difference. And this will immediately give you your galaxy bias parameter. Here's a list of some separate universe constructions. The ones that I'm going to be showing results for are the ones at the top. So for example, total mass perturbations can be mimicked by a separate universe where you play with omega matter. And since this is just an increase in total mass, so you only change omega matter. If you keep everything else the same, and if your fiducial cosmology was flat, this will generate spatial curvature. So these simulations are also called curvature simulations. And the other case that's interesting and we're going to look at is the case of gravitational potentials to measure parameters associated with primordial non-Gaussianity. Here, the relevant parameter you can show is a change in AS, the amplitude of the primordial scalar power spectrum. All right, so let me then show you some results. So first, let's remind ourselves of what is it that the parameter space of bias parameter is telling us. And as I write here, the space of bias parameter is a way to organize the different tracers of the universe by their sensitivity to changes in their environment. So here I'm going to be plotting B5 versus B1. And remember from this equation, B5 tells us how sensitive the galaxies are to gravitational potentials in cosmologies with FNL. Just indulge me on this fact. I'm going to define FNL a little bit later on, but this is a way to quantify the departures from primordial perfect Gaussianity of the initial, the spatial distribution of the initial fluctuations. And B1 is the same thing, but for mass density perturbations. So this is the relation for halos. So to be concrete, every dot here shows the bias values of halos in some total mass bin at some redshift. Here I'm not distinguishing the mass values and the redshift, not to clog the figure too much, but in general, mass and redshift increase with increasing B1. So now this is a result that has been known for quite some time, and clearly is not the most interesting thing we can do with a simulation like illustrious TNG, where we have galaxies, not just halos, at our disposal. So something that's a little bit more interesting is this result in red, where I'm showing the same thing, but now for galaxies in stellar mass bins. And this is the case of the neutral hydrogen distribution, which you can also model and evaluate the bias parameters using separate universe simulations. So clearly, different traces of the logical structure display different bias parameter relations. In particular here, according to the illustrious TNG model, this model is telling us that the bias relation, this particular bias relation, has a higher amplitude for the galaxies compared to the halos, but the H1 behaves in a different way. It's actually below the relation of the halos. So this is the result in itself, but I think it's interesting to try to understand what's the origin of this upward shifting for the case of the galaxies and downward shifting for the case of the H1. So as usual, when it comes to interpreting results from simulations, we very often rely on the good old halo model to build intuition. So the starting assumption of the halo model is that galaxies live inside halos of some mass, which is as good as an assumption as it gets in our fields. And then, under this assumption, the bias of the galaxies then becomes a combination of two effects. The first is the bias of the halos, which, remember, from the definition of bias, tells us how many more halos are going to form inside the perturbation compared to cosmic mean. But then we have this other term that I'm calling occupation bias or occupation response function. That's also another game. Another name we use for it, which tells us now instead how many more galaxies form inside each halo, inside the perturbation compared to cosmic mean. So in this cartoon here, you will notice that the perturbation is modulating not only the number of halos represented by the purple circles, but also the number of galaxies that live inside each halo that I'm representing by these red stars. Oh, it turns out I also have another slide with equations, but I think this is the last one, maybe. So maybe just a shout out for the experts. If you work on this area, I'm sure you've used or seen an equation like this in papers or in talks, followed very likely by a sentence saying something like the bias of the galaxies, BG, is an integral over the halo mass function, and the galaxy halo occupation distribution, the mean number density, the mean number of galaxies that live in halos with mass m, and then the halo bias. So you are weighting the halo bias, and the weights are the halo mass function and the galaxy occupation distribution. The derivation is actually quite simple, and you can look for the details in this paper, but let me just argue in words for why this equation is incomplete. So what we have here is an integral over the halo mass function, the HOD stands for halo occupation distribution, and the halo bias. And again, remember the definition of bias is telling this is the response of the halo mass function to changes to large scale perturbation. So clearly we're missing the same response of the HOD, and that's precisely what these occupation bias terms describe. So you can write down effectively the same equation for the case of the H1. Instead of dealing with the galaxy occupation number, now we deal with the H1 content. This is the H1 to total mass relation, and you have equivalently the same or a similar H1 content bias function. Long story short, I don't need to show these plots for brevity. Just believe me that in illustrious TNG, you can measure these coefficients here also using separate universe simulations. Turns out that for gravitational potentials, these numbers here tend to be predominantly positive. These ones here tend to be predominantly negative. We can go into the reasons why as well. That's also very well understood. But ultimately, the fact that this is positive and this is negative is what explains why at the level of this B5, B1 projection in the space of bias parameters, the relation of the galaxies goes up compared to the halos, and the relation of the neutral hydrogen goes down compared to the same halos. All right, that's all that I wanted to say concerning the separate universe part. Let's switch gears and go to the galaxy forward modeling side. So the ultimate goal of the forward modeling approach is the following. They wish to reconstruct the initial conditions and the cosmology that gave rise to a real-life galaxy sample in the universe. So step by step, the way this is done is you start off by generating a random realization of your initial conditions. You evolve that under gravity to form the forward evolved mass distribution. Then you use this to compute all the operators that enter your bias expansion. You sum them up, multiplying the bias parameters to generate the forward evolved galaxy density fields, which you can then compare, importantly, at the field level with the observed galaxy distribution. And then you simply iterate, sampling over the phases of the initial conditions, the cosmological parameters, and the bias parameters. So, of course, there are some pros and cons here. And you can clearly tell my bias from the way I'm referring to the pros and the cons. The disadvantage is that this is clearly very numerically intensive. And this is not only because you need to solve an n-body simulation to sample one point in parameter space, but the parameter space itself is very high dimensional because of the need to sample the initial conditions. If you think of describing the initial conditions on a grid that has like 100 nodes on the side, this immediately gives you at least 1 million parameters you have to sample for. But nonetheless, there are ways to do that. This is numerically intensive, sure, but there are things like Hamiltonian Monte-Carloing that allows you to sample these very high dimensional parameter spaces. The significant advantage is that at the end of the day, despite after all the numerical intensity, you're met with the comfort of knowing that you are utilizing all of the information in the data because you're doing the inference at the field level. And this is such an important point that I have one more slide just to contrast the current way we infer parameters from our galaxy data and the forward model way. So the current way is called summary statistics approach. And the key idea is that we start from our observations, and then the first thing we do is to compress it into a set of summary statistics. More often than not, that ends up being just the 2-point function. And now, because our observations are non-Gaussian, clearly there's information beyond the 2-point function. So the 2-point function, and for that matter, any finite set of summary statistics will always leave some information out. So if you only do your inference at the level of the summary statistics, you're not utilizing all of the information. And the goal of the forward modeling approach is to bypass the need for any summary statistics by making directly forward modeling predictions for the actual galaxy density field and not any summary statistic of it. So that's the dream, that's the goal. There's still a lot of work to be done, but something that we can do in the meantime that's a lot easier is, rather than focusing on observed galaxies, we can turn our attention to simulated ones. And if I'm just interested in galaxy bias parameters, this makes my life a lot easier because I don't need to sample the initial conditions because I generated them to run the simulation. And I also do not need to sample the cosmological parameters because I chose them to run the simulation. So I can fit way more efficiently just for the subset bias parameters and study what are the bias parameter values for galaxy formation model A, B, or C. And here we're going to look at results from Illustrative TNG. So now I'm going to show results for 3 other bias parameters. Well, B1 we already saw. Now we're going to be looking at the quadratic density 1 and the tidal bias 1. Remember, so B2 versus B1 on the left is the sensitivity to second order to mass perturbations and to linear order in the x-axis, and on the right we have in the y-axis the sensitivity to tidal fields versus the sensitivity to mass perturbations, VK squared versus B1. So this is the result for galaxies in total mass bins, galaxies in stellar mass bins, galaxies in bins of the mass accretion rate of the supermassive black holes that they host, colored specific star formation rate bins. We can try to understand some of these differences here based on halo occupation distribution response functions as well. But for short, I just want to color all these points in gray. Let's think of them as a generic prediction of all of the galaxies that exist inside this illustrative TNG model, and compare with these recent observational determinations that exist for these 3 bias parameters using real-life galaxies. And I really like this figure because it gives me a chance to call back to the 2 main motivations we have to study galaxy bias. So on the one hand, we can appreciate that the precision of these predictions, okay, there's some scatter, but it seems to be under some control. And it's clearly smaller than the scatter we have between different studies and also the size of the corresponding error bars. So we can start asking the question, and answer it, obviously, how much would the constraints on cosmological parameters of all these studies can improve if we factor in the priors on these bias of relations into their cosmological analysis. Or, as I mentioned earlier, if you're more interested on the astrophysics sides of things, you can turn the argument around and make predictions for other models other than TNG. And there are models, there are alternative models in the market. And if they differ, then we can hope to use some of these or future versions that have determinations of these bias parameters to distinguish between one galaxy formation model and the other. This is before moving on to the last part, just because I mentioned assembly bias in the abstract I sent you. So here's just one slide to make that connection. So the figure on the right is a figure taken from this second paper over here, where we're looking, again, using the forward modeling technique, we're looking just at the bias relation of halos, where we're looking at the assembly bias signal. So the assembly bias is the word we give to the dependence of the bias of halos on anything beyond just their mass. So what we're seeing here in particular, the points with the same color show halos with the same mass. So let's focus, for example, just on the blue ones. All these 4 samples here, they are all in the same total mass beam, but they have different concentrations. The halos become more concentrated in the direction of the arrows. So the key takeaway point here is that for some reason, which we can try to understand, halos that are more concentrated, they are less sensitive to mass density fluctuations because B1 becomes smaller, but they're more sensitive to tidal fields because BK squared gets further away from 0. And in light of this, so this is a simple result from just halos in gravity-only simulation, so no funny galaxy formation going on. But it's interesting to contrast this with some of the relations we're finding for galaxies on the left. So here the premise, which is something we're looking on at the moment, is that if these different galaxy types populate at fixed halo mass, halos with different concentrations differently, then some of these differences here would naturally propagate to the bias relations of the galaxy, thereby explaining why on top of occupation bias terms, providing another possible explanation for the origin of differences of bias relations between different galaxy types. Okay, so in the last few minutes that I have, let me then comment on some of the consequences and the importance of having a good knowledge of galaxy bias, in particular in tests of inflations through searches for primordial non-Gaussianity. So as promised, here's the definition of FNL. Is this equation over here. So phi denotes the primordial gravitational potential. And without generality, you can always write it, expand it in powers of a Gaussian random fields. If you multiply the square term by some coefficient that's non-zero, then if you add a Gaussian random field to its square, it generates a non-Gaussian field. So FNL is this way to parameterize departures from perfect Gaussianity of the initial conditions. So the reason why FNL is a very popular parameter is because, as you can imagine, different values of FNL will let us distinguish between different models of inflation, and in particular, detecting FNL would allow to the simplest single fields models of inflation and open up the door for more elaborate multi-field scenarios, which a lot of people would find very interesting. The current tightest bound comes from the CMB, Planck 2018, compatible with 0 with an error bar of 5. And the next improvements over this are expected to come from future galaxy surveys, who have been promising, if everything goes well, to reach volumes that will allow us to probe FNL with a precision of order unity and maybe below. So there are 2 ways to constrain FNL using galaxy data. The main one is using the 2-point function or the power spectrum. So here on the right, you see in gray how the galaxy power spectrum would look like if the initial conditions were perfectly Gaussian. But if we have FNL, then you can show that there is this additional contribution that scales as 1/k squared, and which generates this very specific scale-dependent signature on large scales, whose amplitude is what we can use to constrain FNL. The problem, and you can kind of see what I'm going with this, is that the amplitude of this signature, which is what we want to use to constrain FNL, is proportional not only to it, but also to these bias parameters B1 and B5. Now, the fact that B1 appears here, it must be said, is actually not too scary, because B1 also contributes on small scales where FNL doesn't. So you can use the smaller scale parts of the data to constrain B1. But even if you know B1 exactly, using just the signature alone, there's no way around it. In order to constrain FNL, this cosmological parameter, you're forced to make some assumptions about B5. The second main way to go after FNL using galaxies is using the galaxy bispectrum, the 3-point function. And long story short, even though here the degeneracy is not perfect, to a large degree, any competitive constraints on FNL are still plagued by this perfect degeneracy between that cosmological parameter, B phi, and this additional bias parameter, B phi delta, that appears at second order, which we have to, since we're dealing with the 3-point function in this case. So now this begs the question, how is it that all these past works that we know exist with both real data constraints on FNL and many more works that exist with forecasts for FNL, how is it that all these works have claimed to be able to constrain FNL? And the answer is these works have assumed these so-called universality relations. So these relations are shown here in solid black. And the key idea is, since you can use the smaller scale part of the data to fit for B1, if you assume that these relations are true, then you fix the values of B phi and B phi delta. They are no longer free parameters. So the degeneracy with FNL is broken, and you are free to constrain FNL. The problem is that these relations are derived under an incredibly set of simplified assumptions. They assume universality of the halo mass function, which is not even true. And that's where the name comes from. So despite being routinely used, there's really no reason for us to expect. And in fact, we have all the reasons to expect this relation not to hold. And our simulation results with Illustrative TNG have been confirming precisely that. So this is we saw some of these results already. This is the case for objects selected in total mass bins, stellar mass bins, black hole mass accretion rate bins, where things get even crazier. And this is the case of the H1. So just to flip between them, this is the level of scatter that we have between different traces. And you can see that the universality relation is never a good description. So in light of this uncertainty over here, and I want to stress this is just the first set of these simulations. So a lot more work is needed on obtaining more simulations, refining our selection strategies of the simulated galaxies, as well as making the same measurements for models of galaxy formation beyond Illustrious TNG. But still, the universality relation is not going to be very clearly a good description. And so we should start asking ourselves, to which extent are all our constraints or forecasts or expectations on FNL incorrect, in that we've been using the wrong assumptions about galaxy bias. This sounds like a provocative question to ask, but it's perfectly fair in light of these results. So at the end of the day, even after all this work is done, we'll always be living with some uncertainties on the bias relations. So this is going to affect the resulting constraints on FNL. So we should start asking, how is it that or how do these bias uncertainties propagate into FNL constraints? So I'm going to show the outcome of a simple idealized forecast analysis. You can look for your favorite specification if you work on this area. Here, the key point is that I'm going to generate a fake data vector of multi-tracer power spectrum and bispectrum data with some fiducial cosmology, which is going to have a value of FNL equals to 5, assuming some bias, some fiducial bias parameter relation. And then I'm interested in knowing how do the MCMC constraints on FNL depends on what I assumed about galaxy bias. So the result is currently on screen shows the marginalized constraints on FNL if I assume precise knowledge, but of the wrong bias relation. So concretely, what I'm showing here, I generated the data vector assuming a line that goes through the red points. But in my MCMC constraints, I'm assuming that the solid black line is the truth. And since I underestimate the B phi B1 relation, given that B phi and B1 are nearly perfectly degenerate with FNL, I overestimate FNL to compensate. And this is what happens as I do the same thing, but instead of assuming precise knowledge of the wrong bias relation, I keep my bias prior centered around the wrong thing, but I marginalize over a Gaussian prior. And this is what happens as I increase the size of the prior. So this is a choice of size tuned to ensure unbiased constraints, which may look at first sight like good news. But as I keep increasing the size of the prior, contrary to what one might naively think, increasing the size of the prior is not conservative. It doesn't just increase the error bars, it can also bias your result again, and this has to do with projection or so-called projection or volume effects. So long story short, what's happening here is that as your MCMC chains get closer to the FNL equal to 0 direction, because B phi and B phi delta multiply FNL, if FNL is 0, B phi and B phi delta are unconstrained. So the wider your prior, the longer the MCMC chains are going to spend around the FNL equal to 0. So the more volume you put around the FNL equals to 0 direction. And so after you marginalize, you progressively bias your constraints. So in the case of FNL is a prototypical example of the importance of having good, robust priors on galaxy bias. We really need our simulation predictions to be not only accurate to save us from these types of biases, but we also need them to be precise enough to save us from these projection effects. And this is an issue that is massively, in my opinion, under-discussed in the literature, and which we should start revisiting and correct correspondingly our expectations for FNL. Okay, this is my last slide. I hear some of you asking then why the obsession with FNL? Why don't we just fit for the products of FNL times B phi and FNL times B phi delta, which are the parameter combinations that entered actually in my galaxy power spectrum and bispectrum predictions. So the key advantage of this is that this bypasses the need to make any assumptions about the bias parameters. And although it's true that it comes with the disadvantage that you will not be able to constrain directly the numerical value of FNL, the silver lining is that you can still distinguish it from 0. Which is still interesting in that if you detect non-zero FNL times B phi, this will still allow you to rule out single field inflation, which will go a long way in improving our knowledge of the early universe. You wouldn't then know, fine, which multi-field model is the right one, but you'd have discovered something. There's a disadvantage that I don't have the time to go into, but I'm happy to answer questions if you work on this. When you choose to parameterize things in this way, you can show that the bispectrum will no longer be as useful. So you might as well just run constraints using the power spectrum. But yeah, if you work on this, or if you know someone who works on this, or if you're going to work on this in the future, I beg you to start alongside quoting bounds on FNL, to start also quoting bounds on these parameter combinations, because this is truly what the data is constraining. Anything else is going to be dominated by your prior assumptions, and we generically do not like the cosmological constraints to depend heavily on what we have assumed. All right, so this is my last slide. Here are some 3 key takeaway points and some key selected figures. I'm not going to go through this to save time for some questions. And yeah, thanks for listening, and I'll end here.
Thank you, Alex. So are there questions? Go ahead.
Hi, Alex. Tessa again. Can you give a bit of an indication going forward with the next generation of surveys, things like Euclid and LSST, are bias parameters of any